Okay. Yeah, basically I was just asking myself, am I muted? Am I not muted? Always hard to know, because I hadn't checked. Okay. So today, I'd like to cover a little bit about red-black trees, and we're going to also do splay trees. So I assume that everyone is done with the project, right? So let's see, let's open the splay tree visualization, because this is what we're mostly going to talk about. So yeah, basically, there were two main questions that people were asking pretty consistently, and well, I gave the wrong answer, but then I finally fixed myself. So we have two. So project updates. Number one is that you must consider the case. Consider m times n is not equal to array size. So basically, if mn is equal to array size, that's one thing. If mn is not equal to array size, then there are two other things that you can do. If mn is bigger than array size, then you can basically just ignore the rest of the array. And if it's less, then you fill the rest with zeros. So it's actually not the worst possible thing to do. It's just, it hurts my brain a little bit, but really it shouldn't be a problem. You just have to make sure that your code will function with that. The number in yes, if basically the length of array is always going to be array size. If not, then that will be a seg fault, and or some kind of memory error, and that would be the caller's fault, right? So you're giving them the parameter to save themselves. They have to tell you the truth, right? In C++, sometimes you just have to tell the truth. You can't pass an array and be like, oh, this array is twice as big as it is, because then the function that's using the array will just simply scan through it and could potentially, do some bad things. The other thing is that what if the sparse ratio, or what, not really what if, what is the sparse ratio of an empty CSR? And the answer to that is 0 or 100. Okay, why won't it draw? Come on, don't screw up on me. Okay, I'm unplugging this and plugging it back in for a second. Okay. The answer is that it doesn't matter, because it's kind of undefined. And so basically the point of this is that whatever you return, just make sure that you check if m times n is equal to 0, right? Or really m underscore m times m underscore n. If this is true, right? If this is true, then you want to not, don't return, because in the end, remember, you're going to have to divide by m underscore m times m underscore n. And if you do that, when one of them is 0, then you're going to end up with a 0 division. So don't do that, right? And so like the sparse ratio is really more undefined for an empty object. Now that isn't to say that if you just have an array of all zeros, for instance, if you have a matrix of all zeros, its sparse ratio should just be 100, right? Because it has no m non-zeros, the size is non-zero, so it's okay. So non-empty is not equal to all zeros. Non-empty is just if this is true here. So the other thing to say is that what about the average sparse ratio? And so what you want to do is, as you're scanning through the list, skip any empties. So as you're scanning through the list, I guess don't count them. So don't just use m size in the end to divide by m size, maybe. You actually have to do an m count, or you actually have to count up the number of non-zero things, and then it's like you sum up the sparse ratios of the CSRs. Okay, so those two questions came up. I think that's basically it for the project. Hopefully this one is not a big problem. The only thing you might have to consider is that if you're using an array that goes up to array size and mn is less than that, then that'll create a problem here. This one is a little bit more annoying, but I only had to modify a few lines of code to actually make it work. So it should be doable, just reminding you that you have to do it. And then the average CSR sparse ratio of any empty is just, I don't know, 0, 100, who cares, right? Just return a number, don't get a 0 division error. Okay. I mean, technically you might want to throw an exception, except for the fact that we didn't tell you to throw an exception in the project. So I would just recommend against throwing an exception. Fill the rest with zeros. Okay. So let's begin to talk about other things today. So what are we going to talk about today? Basically today, I think what we're going to talk about is, we might talk a little bit about AVL again. We'll talk about Splay Trees. And then a little bit about red-black trees. And so today I would like to, let's see if we can spend most of the time on Splay Trees. So today was supposed to be mostly about red-black trees, but I've changed my mind for various reasons. And I guess you'll find out those reasons like tomorrow or today or something. Actually, I guess I'm curious. No, not yet. Okay. All right. So, but anyway, let's start with Splay Trees today, and then I might go back to Avl Trees to do a little bit of extra talking about AVL, and then if I have any time, I'll do red-black trees. So that probably means probably not, right? Because whenever I think, oh, if I have extra time, I'll do this, then I never have extra time. So let's just remember, right, what an AVL tree is, right? An AVL tree is a binary search tree where the one rule is that the height of any node dot left minus the height of any node dot right, well, the same node, I guess, is less than or equal to 1. So what that means is that the height of the left side of the tree and the height of the right side of the tree differ by at most 1. So it's okay if, for instance, the height of the left is 5 and the height of the right is 4, or it's fine if the height of the right is 10 and the height of the left is 9. Those are all okay. The problem would occur is if the height of the left subtree were 8 and this were 10, or bigger than that, could be 12 or 15, right? So for instance, like this thing here is not an Avl tree because the height of this node here, well, let's just say that we start at 1. And so if we start our node's height at 1, then the height of this node is 2, because it's the, remember that height is defined as the max of the heights of n dot left and height of n dot right plus 1. So the height of a node n is equal to the maximum of the two heights of the subtree. So for instance here, the height is 1 because it's 1 plus 1. Technically there's a height 0 node here, right? But we don't care. And then the height of this thing is, so the height on this side is 0 because this is a null node. The height of this thing is 3, but it's not the fact that this is 3 that's bad, right? 3 is not a bad number. It's really the fact that this node here disagrees here. It says, I got a null on one side whose height is 0, and I got a non-null over here whose height is 2, and 2 minus 0, the absolute value of that is, you know, this is the rule, and it's not true. So that's the rule that an Avl tree has to obey in order to be an Avl tree. So we learned a bunch of rules to fix, well, we learned basically the rotate left and rotate right operators. And there's really, what, like 4 cases. There's the case where you have this going on. Well, so there's the, I'm going to call, so because we're about to branch into splay trees, I'll call this the zig-zig case. I'll call this zigzag. This is the, I guess if we're naming it this way, this could be like the zag-zig. And this here, you might also call this zig-zig if you're willing to embrace symmetry, but we could also call this the zag-zag case. And so, really, what all this means is that in order to make this an Avl tree, if this is the heavy side, right? If this is what you do is you rotate this node up to be the top. So this becomes this structure, and then you're happy. Now, if this is the structure, then what you do, and let me color these nodes just so that it kind of makes more sense. Let's make this one blue. Let's make this one purple. And then let's make this one yellow. So if these are the colors of the nodes, the first thing you do is you rotate this node this way. And so then what ends up happening is that you reduce this thing into a case, you reduce this into this case here. So let me draw this out. This is a purple. Then we have yellow in the middle here. And then we have blue up top. And so just remember that, you know, if you have, and then the point is that once you have this case, then you get to rotate this node this way. And so what you end up with in the very end is yellow on top. You end up with blue here, and you end up with purple here. And so these two so this operation is actually, I'm sorry, this is not called a zig-zig because it's only one rotation. So this would actually only be called a zig operation, and this would only be called a zag operation. I'll show you what I mean by zig-zig when we get to splay trees in just a minute. And then let's do the same thing again. And so remember when you rotate this kind of thing, right? So basically the idea here is that these all have subtrees, right? But how do these circles get to be the circles and then everything else gets to be the triangle? The answer is that this thing has the biggest height. So this height is bigger than this height plus at least 1, right? So it's bigger than that height plus 1. And then this height here is bigger than the height of this tree node here. So we always, the rule in an Avl tree is that the nodes you select are always the heavy side nodes. Okay, so you always go down the heavy side of the tree. So, and that's why we have all these different cases, right? Because if you're in the case where, for instance, the blue node has a height difference, so for instance, if this height on this side is like 4, and this height over here is actually 2 for this subtree, then this is the one that gets the circle, and that's the one that just becomes the other subtree. So here, let's make this purple again, and then let's make this one yellow. And so remember what you have to do is you have to rotate this node like this, so what you're going to end up with is yellow in the middle again, so you're going to end up with a yellow in the middle, purple going down the right side, and blue still up top because we haven't touched blue yet. And then what you do is you rotate this node this way. And so when you do that, what's going to end up happening is that yellow becomes the root, and then purple becomes the right child, and blue becomes the left child. And so remember, basically what we're doing here is that the reason why this works is because let's say that this tree has a height of 2, and so this tree here will have a height maybe of 3, and so this tree here is going to have a height of 2, right? The child of this tree. So for instance, when we move this over, we're going to end up with 2 children here, each of a height 2. Why wouldn't switching the nodes put the purple on the left side? So the thing is that you have to remember that this is always still a binary search tree. So at all times, there's actually values in these nodes, and not just heights, but there's also values. So for instance, this could be, say, 7, and then this could be 12, and this could be 9, right? So the thing is that in this case, when you make the binary search tree, there's only one way that this can ever really go, right? 7 always have to have 9 and 12 on the right, to the right of it. And so that's why we can do something like this where we go, this will be 7 here, and this will be 12 here, and that's okay because now this is 9, and so the correct node is always to the right of the other node, right? Because 7 is less than 9 is less than 12. And then here we're going to get 9 as the root. And then we get 12 over here and 7 over here. And now these are not the heights. These are the values in the specific nodes. And so that's why everything kind of has to be the way it is, because we have to, basically, you have to view it as like 2 competing interests, right? One, we want to keep this thing always a binary search tree. If this thing ever fails to be a binary search tree, then the next time you go to search for a node, you run into problems. You can't find the node that you're looking for. So that's a major problem. But then on the other side, you want to maintain these heights. And so basically you have 2 different things. You have the values of at every node, and you have the height at every node. And so that's, that is what it is. Okay. And then the last thing that you can do here is this is a rotate right operation. I'm sorry, rotate left. I can't tell left versus right. right? This correct. This is a ROT-L operation. So that is how that works. So these are the basic cases. Yeah, we can look at the visualization again. So let's pull out the Avl visualization and just go through it one more time. Where is the Avl? It's right here. So let's make our node 20. Oh, here's something cool. I didn't realize you could do this with the simulation. You can actually use letters, but let's insert D. Cool. And then let's insert A because A is less than D. And then let's insert F because F is bigger than D. And so, okay. Now let's insert G because G is bigger than F. And you see that here, no problem, right? No problem yet, because the height difference of these two nodes is 1. The height difference of this node and this blank space, right? The blank space has a height of 0, so the height difference here is 0. I'm sorry, the height difference here is 1, so that's okay. The height difference between these two children, right? I know that you're like, well, but it doesn't have children. Exactly. The height difference between these two children, both have heights of 0, is 0, so thankfully null nodes are never going to need any rotations, right? Because that would be a problem. Now let's insert Z and see what happens. So I'm going to slow down the rotation, and we're just going to watch as what happens. So when we insert Z, it's going to insert like a normal binary search tree. So Z is bigger than D, bigger than F, bigger than G. So it's going to become the right child here. And then we're going to look at our cases, right? And we're like, which case are we in? Right? Oops, sorry. Avl, not red black yet. So let's just let it insert. So we're in the zag case, right? So what happens when we're in the zag case? Right? So what's going to happen is it's going to insert, and then here it's okay, right? Here it's like, oh, I'm fine. And so, but then it updates the height to 2, but it doesn't care about that right now. And what it's going to do now is it's going to pop back up to this one, and now here's where we're going to actually see the problem, right? We don't see the problem here because we're too low. The height differences of the children are 0 and 1, so that's okay here. But you have a feeling like with a height of 2 here, and you don't see anything over here, you're going to run into a problem. But again, you don't know that until you pop back up to the parent. So now at the parent, you say, oh, wait, my height is now 3, right? But that's not actually the problem, right? The height isn't the problem. The fact is that the problem is that one of my children, my right child, has a height of 2, and my left child has a height of 0, right? That is the problem. That's what we have to fix. And so now we go down again. We say, who's the heaviest child? The heaviest child is G. Who's the heaviest child? The heaviest child is Z. And then we say we're now in a zag condition. So now we rotate G up to be the new root of this little subtree here. And there we go. Right? That's a zag. And then here it's a difference of 1, so it doesn't have to do anything. So let's increase the animation speed, and let's insert ZA. Well, let's insert Y. And so Y is going to insert here, insert here, insert here. And then what's going to happen? So are we going to have a problem here? I think the height here is 2, the height here is 1, so no problem. Then we're going to go back up here. We're going to update the height. The height's 3, no problem, right? Because 1 and 2. Now we're going to go back up here, update the height. The height is now 4. But again, we don't care about the height where we are. We care about the height of the two children. Now, what happened here, right? What happened here? What happened here is that, do these rotations also occur when you delete a node? Yes. So you notice that this is the heavier side. And so what you're going to have to do, well, I should step forward, step forward, step forward. Insert the node, update height, update height, update height. And then, what you need to do is you see that the heavy side here is 3, the heavy side here is 2. So this is actually still a zag condition. So a zag condition says you rotate left again. And so once we rotate, there we go. So, okay. Let's insert a bunch more nodes really quickly. Let's say insert J. Let's play it. Let's insert R, T, S, V. I know that it's all going very quickly, but just forget that for just a second. Maybe Q. Let's see. How do we? So watch what happens when we delete V. Now let's slow it down again, right? So we see that the Avl tree has kind of maintained balance and done all this stuff properly. So what happens when we delete V? So we could also delete some other node, but really the answer is we're always deleting a leaf node. So let's delete V. And so what we're going to do is we're going to find it. So we find it as usual, right? And then we delete it. Okay. And you notice that actually we recheck all the heights and nothing has gone wrong yet, right? Because the height here is still 2, even though we just deleted a node, the height here is still 3. Everything stays the same, right? Everything stays the same. Now what happens if we delete Z, right? That's the real question. So it's going to find Z as usual. So it goes down into the tree and it finds Z, and then it pops it off. But now what's going to happen? What's going to happen is that as we delete this node, it's going to see that there's a problem with the heights, because now we're going to have a height of 1 and 1. So at this point, it's just going to update the height. No problem yet. Then we go back up here. Well, update the height. No problem yet, right? And then we step back here. Oh, actually, I'm sorry. There's no problem yet, right? Because you see here the height is 4. Here the height is 2. Here the height is 3. The difference between 2 and 3 is 1, so it's still okay. All right, so now let's delete Y. Let's delete Y. Skip. Cool. Y goes away. Now what happens? So this is what's really going to cause an issue. What happens when we delete S? So when we delete S, we see that this height is going to update to 1. On this side, it's going to be 3. Right? That's a problem. So let's delete S. So it's finding S. It's going, let's see, play. So it's going to step down to S. It's going to kill it off. And then once it updates here, so let's skip back and delete S again. Let us pause it and then step forward, delete the node, update the height of T, and then when the height of T doesn't cause a problem. What causes a problem is when we go back to the parent is R, then we see that there's a height disparity. And you might be thinking, wait a second, isn't there a separate algorithm for maybe delete fixup versus insert fixup? And the answer in an Avl tree is no. The algorithm is the exact same for both. So here you see that the height here is bigger than the height here, and they differ by more than 1. So here's an unbalanced situation. So then I go down to G, and I say, you're going to have to rotate right in order to fix this problem. So what's going to happen? So G is going to keep D, but G is going to make R the new parent. I'm sorry, G is going to make R the new right child, right? So G is going to make R the new right child. But because R didn't have a left child anymore, then we can attach J and Q in there. So what's going to happen is R is going to come down here, J and Q are going to attach themselves to R, and G is going to be the new root. So let's see what happens. Yep. So G keeps D, R becomes the right child of G, and J attaches itself to R like this. Right, so that's kind of the idea here for these rotations. So basically, the idea is that okay, animation complete. So whenever it sees a height imbalance, it doesn't matter if the height imbalance is on insertion or deletion. right? So if we then delete A, and so if we basically skip forward, it's just going to delete A. But then if we delete F, what's going to happen? So we're going to see that when we delete F, this height is going to become 1, and then we're going to actually be in a like a zag-zig condition, because the highest thing is now to the right, to the left, right? When you descend 2, it'll go down to the right, and that's the highest thing, and then you go down to the left, and that's the highest thing. So what's going to end up happening is that it will, so once it gets rid of this node, it updates the height to 1, it sees the height imbalance, and then it does a zag-zig. As I say, you do not have to search the tree for height differences. You don't have to search the whole tree. You only have to look along the insertion or deletion path, and as you pop back up, you check, right? All you do is that you check, wherever you are, you check the left child and the right child, and you ask, how high are you? And they both report their heights back, or if they're null, they report 0. And then what you do is you say, okay, if all that's the case, and the height is different, the difference in heights is bigger than 2, then you have to rebalance. And so basically what you do when you know you have to rebalance is that you track down 2 in the highest direction, and then you pick the case you're in. And that's what tells you what to do, right? So basically insertion and deletion, like insertion into an Avl tree basically follows this. You insert into tree, and then what you do is you update heights, check for imbalance, and if there's an imbalance, then you go down and find which case you're in. You're either in the zig case, zigzag, right? Zag-zig, or zag, right? Those are the 4 cases that you can be in. And we've drawn the cases out, so I won't belabor that anymore. So basically you figure out what case you're in, and you go down along the highest path. Now for insertion, the highest path is always going to be the insertion path. For deletion, the highest path is generally going to be the opposite path, right? Because if you've deleted something, you might be decreasing the height, or you might not be decreasing the height, right? Because if you kill off one child and there's another child, then it doesn't decrease the height of the parent. And if you have one child left and you kill that one off, then it does decrease the height of the parent. And then the parent might be, again, when you go up to the parent's parent, it might be they're too high or too low. So you just have to trace along the highest path. So whatever the highest path is, you go down and you find the child and the grandchild, right? And then if it's zig, you rotate the child. If it's zigzag, you actually rotate the grandchild. And so these two rotate the grandchild, and this one just rotates the child. And then what you do is then you go up to the parent, so you pop up one level. And then you do, well actually, let me just say it again. I know that you might think it's redundant, but actually it's not redundant. So before you pop up to the parent, you actually update heights again. So that's something that you have to remember if you're ever going to do anything like this in actual coding, is you have to update the heights, check for the imbalance, do the rotation, and then re-update the heights. Don't forget to do that, because the point is that once you pop up to the parent and then you do this while parent is not equal to the root, right? basically, or really, well, parent is not equal to null because the parent of the root should be null, right? So while the parent node is not null, you pop up to the parent, and then you repeat this whole process. You update the heights, check for imbalance, you go down, and you find out what case you need to do. And it's possible that if you find out that you don't have to do anything at that case, then you just go up to the next highest level and update heights, right? So it's possible that if there's no imbalance, you skip the step to, you don't always have to rotate. Sometimes you might find that there's no imbalance, so you don't rotate, and at that point you don't, I guess, need to update the heights again. You just pop up to the parent, update heights, check for imbalance. If you have to do anything, you do it, and then you just repeat the process. So this is the AVL process, and this is the process for both insertion and deletion, right? So I could just say delete from tree as well. So like basically, a lot of algorithms will call, what they'll do is they'll have their insertion method, and at the very end of insert, they'll just call like AVL fixup, which will do this process. Okay. So all of that is AVL. So now let's take a break from AVL and let's talk about splay trees. So splay trees are kind of a, I guess they're kind of a gimmick. They're a little bit cute. So here's the idea. Whenever you insert and I'll put a little star on delete, or find, with a little star on find, you can't spell splay. You splay the tree, or you splay the node, and of course I'll put a star on that, to the root. So this is like an AVL tree, except that every time you perform any operation on the tree, you will move that that node that you found up to be the root. So let me show you, let's just do the Splay Tree visualization first, and I'll show you what I mean by this. So let's insert F, that'll be our root. Then let's insert A, and I want you to watch, I'll slow it down just a bit, but you're gonna see what's gonna happen. So we're gonna insert A, and then A's are gonna become the root. So we're going to rotate to the right, so that, there we go. So that A is the root and F is now the right child. And you're like, well, why did I just do a rotation? This tree wasn't even that imbalanced. It doesn't matter. There's no height anymore, right? So we don't keep track of the heights. You notice that there's no heights anywhere here. Nothing is getting updated. It just says wherever the thing inserted, splay it up to the top. So for instance here, I'm going to insert, like, say, H. So H is going to insert like in a regular binary search tree. And then you see that here, yeah, it doesn't keep track of the heights. So for a splay tree, it doesn't care about heights. It always just makes the thing the root. So let's insert H again, and then let's pause it here, and then let's step forward. So it detects, so you see here what it's detecting, and you're like, well, what does this mean? What this means is that it's detected that it's in a zig condition. So what that means for a splay tree is that the node that we've inserted is to the, well, I guess it's to the right and to the right? So what we need to do is we need to basically rotate this up to the root. So the way to do that is first you rotate F so that F is the parent, and then when H is the right child, then you rotate H up. So basically you perform two rotations. Now, a splay tree kind of, they do these two operations, they kind of compress them down into what they call the zig condition, but actually it is just two rotations. It's rotating until you have F, and then the two children are A and H, and then it rotates H up and then puts F as the left child. So this is truly just 2 rotations, and so that's how they do it. And then let's insert C, I guess. So if we insert C, what we're going to see is the zigzag condition. So let me show you zigzag. Zigzag is, here we go. Yes, this will be a zigzag condition, and the reason why is because it is, first what you have to do is you have to rotate left on, I guess, A, so that C becomes the root. So this will line everything up, right? You'll have A, and then C is the parent, then F is the parent, then H is the parent. And then what you're going to do is you're going to rotate F down, so then you're going to end up with this configuration. So this is like 2 rotations in one, right? This is like a rotate left and then a rotate right. And so that's generally how you do it. So you can always make this a little bit shorter by not doing the rotations, but actually by just like skipping all those steps. But I tend to always view it as rotations. So you're rotating this to the left, and then you rotate C to the right again. So you basically rotate C left and then C right, and that'll take you up to this condition. Now the thing is, we just inserted C, so it has to become the root. So in this condition, we're in a zig condition where we have to basically push this node. We have to get this node up to the root. And so what you have to do is you have to rotate this node to the right. And in order to rotate it right, then H becomes the child here and F becomes the left child. And that's how that tree splays. So every single time you insert, this is what happens on a splay tree. So, okay. You might also ask, well, what happens if you find an element? Well, you splay on find as well, okay? So let's say that we want to, well, let's insert, yeah, basically splay trees are an inserted head, but the problem, you're right about that. The only problem with trees, right, is that a tree, you always have to insert at the leaf-most, child-most node. Oh, I mean, what's the most efficient and fastest tree? Probably, oh, what happened to the stream? Okay, it's back. I would say probably red-black. But AVL is usually like 95% good enough, right? Splay trees are weird, right? Splay trees require something called amortized analysis to prove that they usually operate in log time, and we can talk about that. Maybe Thursday. So anyway, here what I want to do is let's find F. Well, let's find E because E's not in the tree. So if well, let's find F first, and then we'll find something that's not in the tree. So the idea here is that when you find, you do the find operation just like you would, and then guess what? You got to splay this. So then this has to do it's a zigzag condition. So, or it's a zag-zig, I guess, technically. So what you're going to do is you're going to rotate this one to the right, and then you're going to rotate the whole thing to the left. And so F is going to become the parent, H is the right child, C is the left child. They kind of all do it in one step. So remember, F is going up to the parent, H becomes the right child, C becomes the left. Okay. And now remember what I did was I searched for, well, let's insert Z. Yeah, it doesn't matter if you do, remember what I said, if you insert, if you delete, or if you find, then you splay the node to the root. So you might ask yourself, like, okay, but what if, so what about find? Find can result in 2 things. Either the node exists, right, in the tree, so then you splay it, or node does not exist, in which case, what are you going to do? The answer is you splay on the last node you found. So right before you get to the null pointer, you splay on that node. And it's basically the same thing for delete, because yeah, basically that's the idea, is that, yeah, so the idea of a splay tree, that's exactly right, is that a splay tree keeps basically commonly accessed elements near the top. Right? Because even if you start rotating other things down, then once something's been rotated to the root, it takes a while for it to kind of percolate its way back down. So it can really only descend maybe one level each time. So if something's like the most commonly found element, you have 20 levels, then there's like there's less space up at the top of the tree, but the most commonly used elements are up there. And all the rest of the elements that are less commonly searched are down at the bottom. Until, of course, you find one, and then it splays itself to the top. But then the point is that as you find additional elements, it will that element will kind of splay itself down over time. Or I guess anti-splay. If splay means move up, then anti-splay means move down, right? And so then the next question you should ask is, what about delete, right? Right, because delete kills off a node, so you can't splay that node. And so well, let's watch what happens when we delete. So what it should do, let's insert a bunch of elements so that we have a nice big splay tree. Z maybe, let's skip forward. Oh, Y, play. T, S, Q, B, R, R, A, S, T, Q, A, B, C. Let's see, what's a good letter H? J is fine. Okay, so here's our current splay tree. So let's see what happens if we delete S. Okay, that was too fast. Wow, that was too fast. Let's slow that down. I didn't mean to do that. So remember what you have to do when you splay. You have to go and you have to find the successor of the node. Well, let's insert, well, that'll change the structure of the tree. Yeah, okay, let's delete S anyway. So if we delete S, it's going to try to find S, right? So it searches for S. It finds S, and then it has to find the successor. The successor of S is ST. Okay, so this delete actually works just a little bit differently, but it's fine. I think this is actually using the predecessor for delete. If you notice what it just did, right? Because what it did here was it searched for the element in the left subtree that was the greatest. So what you do is, so you notice that it didn't actually, so it splayed the element up to the root and then it deleted it. Right? And so when it says splay the largest element in the left tree to the root, what is that really doing, right? What that's doing is it's finding the predecessor node. And so because it's finding the predecessor node, it's going to splay the predecessor up to the top. And remember what the predecessor is. The predecessor is the largest element in the left subtree. And so when it splays it up there, then what do we know? We know that we're going to end up with something where the rest of the tree is going to be to the left. So the predecessor is not going to have a right child, which is why we can link this predecessor node up to ST. Okay, so that's why when you splay this thing, so when we step forward, it's going to find the predecessor, it found it, so now it's going to splay it up, so now we have that, and basically ignore this part of the tree for now, right? Just pay attention to this side. You notice that this is the predecessor node from this old tree, and the reason why it's the predecessor is because it's bigger than everything else in this tree, and so you see that it doesn't have a right child. Now, of course, the arrow is not drawn yet, and we're about to relink it. So now let's relink the thing. And so then here we go. Now it can relink. And so the reason why it's important that the thing doesn't have a right child is what? Well, I mean, just think about it, right? If it had a right child, then could you relink it? Well, no, you would have to do something else where you like uncoupled and kind of merged the two right subtrees, and that's a... The problem is that merge in binary search trees is not easy, right? Because if you have two binary search trees, you can't... There's not an obvious operation that just like prunes them and remerges them in kind of very efficient ways. Unfortunately, it is kind of a more aggressive operation. So, but Splay Trees actually have a nice merge operation because you can always splay the, well, anyway, yeah. So, but let's not go through the rest of that. Let's just okay. No, actually, we're done, right? So, yeah. Okay. So that's how you delete. So let's delete Q now. So if we delete Q, well, let's see, QA, right? So QA isn't in the tree, but we'll find it here. So if we try to delete QA, then this is basically the same as a find operation. So what we're going to do here is we're going to say, okay, there we go, there we go, there we go. Didn't find it, right? So what are we going to do? And you're like, wait a second, we didn't even find the thing to delete. And the answer is it doesn't matter, right? It doesn't matter. You splay the thing that you found, okay? So for delete, if you don't find it, you just splay it like it was find. If you do find it, then you have to delete the element and then splay the predecessor and then do this kind of tree merge process. So remember, Q is going to become the root with J and R as children. And then we still have to splay Q, so Q is going to become the root with RA as a child, and then there we go. So this is definitely a weird process, right? Because it's very kind of aggressive, right? So yeah, so now let's delete Z and see what happens. So it's going to find Z and it's going to delete it. Now let's just play this thing so it moves a little faster. Okay, so now it's about to do it, so it's going to remove the node. Well, there we go. Oh, I forget. So there's a different delete operation that your book talks about. So, okay. So the other delete operation that your book kind of talks about involves deleting the node as you would in a regular binary search tree, and then instead of splaying the node immediately to delete it, you delete the node as you would, and then you splay the parent of the deleted node. So that's the other way to do this. So there's basically two different delete operations on a splay tree. This is one of them. The answer is, the good news is you're not going to be asked to do a splay tree delete. So because you're not going to be asked to do a splay tree delete, you don't have to know which one it is, I guess. So which one do we prefer? do we like this splaying of the node, and then you remove it, and then you find the predecessor, and then remerge the trees, or would we prefer the other way? I don't know. So anyway, okay. So this is how splay trees work, right? So splay trees basically, it doesn't matter exactly how the structure of the tree is. What you want to. So let me just say this. What about delete? So remember, if you're deleting something, if you find it or if you don't find it, splay the last node, right? And if you do find it, then you can splay it, remove it, and then what you want to do is you want to splay the predecessor, and then you can relink, relink the trees. Okay. So that's basically the instruction for splay trees, right? Splay trees are basically you just take whatever's in the tree and you pull it up to the root, regardless of, and of course, if you're finding something that you don't find, then you just splay on the last node. If you're deleting something that doesn't exist, you splay on the last node. And then this deletion is probably the most complicated part, where if you do find it, you have to splay it, remove it, splay the predecessor, relink, right? It's complicated, right? Because, because it is. All right. So actually, deletion can be two splay operations. Okay. So what do I want to do next? So there's a few things that I might want to say. So let's not do red-black today. Let's kill that off because it's confusing enough to do 2 different types of trees, but 3 different types of trees would be way too much. So instead of that, I would like to well, incidentally, I mean, that has been the entire point of today. So, incidentally, there was a reason why I'm covering splay trees and Avl trees. So, I guess I'll just say it because you're about to find out tomorrow. The project 2 is basically going to be a splay tree of Avl trees. So if you're thinking, which one do I have to implement? The answer is both. Yes, that's why I've been talking about both of these things, and I have not said a word about red-black, even though this week is the red-black week. Yeah, so this is going to be probably the most impossible, hardest project that I've ever seen in 341. Okay, so yeah, I mean, I don't want to undersell it. It's going to be a lot. So what I'm thinking that I'm going to do And so here's my attack approach to it. I'm actually, so there's one thing. I already did some examples for Avl insert. So so I'm not going to do any more coding about Avl or Splay Trees. I might show you more rotation coding for red-black trees, but anyway, so this is the one this is my strategy. If I were given this project, 1, I wrote some driver code that's going to be distributed with the project. Basically, write the Avl first. Okay, so that's my strat. I'm going to write Avl first, because once you get Avl working, you can implement the Splay Trees basically using almost the same rotation operations, and so you'll have some experience. And here you're going to have to do a lot of height checking. Do not implement the Splay Tree first, because if you implement the Splay Tree first, you can't test. You actually can't test it until you're done with the Avl tree anyway. And then, so my thinking is I'm going to open a partial submit on GitHub Classroom. And I will try to write some basically test files for you, so that you know for 100% that your Avl tree works. So once you're done with that, then attack the Splay Tree. So there's like a pre-3 that I'm going to see if I can get changed in the project. So currently, you have to do all the string processing yourself, but I'm going to try to write the string function myself, the string calculation function myself. So there's some string stuff, and I'm going to try to write that code myself in a way that is good enough to where maybe we can provide it to not just you, but all the students for this project, so you don't have to write that piece of code. And so basically, it's, so you know how Python, you have like a split function that takes a string and just splits it on white space? Basically, I'm going to write something like that for you, but it's a little more complicated because unfortunately you have to split things by these various symbols that are in these files. It's really ugly. I'm going to try my best to get that included in the project either tonight or tomorrow. So, yeah. So basically, this is my strategy. Step 0 is doom / panic. And then the first thing is write the Avl tree. And the good news is, as I showed you, this is how I tested my Avl tree. I literally just sat with my code once I wrote dump, and let me just show you the test code I used that's going to be provided to you. Nope, that is not it. Nope, that's not it either. Don't ignore all of that. Actually, none of that is right. So where did I do this code? That might have said Avl, but don't look at that because that might have been garbage. Let's see, where did I do that? Main, is it? No. I forget. Oh wait, this is CSR. Here's project 2. Here's the code. Sorry, I have so many things up that I don't know where anything is anymore. I'm totally lost in life. So literally, this is all the code that I wrote. I commented out all the other crap that was in the driver, and I just used this. And this will be provided to you. And so this is how you test your code. You pull this up, okay? And you basically run your insertion, okay? And you're like, all right, let this program run. And then here you refresh this tree. And then you basically do this. You're like, enter a new element. I'm going to enter F. Okay. Insert F. Okay. Now enter G. Cool. Insert G. And then you go, all right, let's insert A. Insert A. All right? And that's how you test this thing. You just test it until you, and then what you do is you make all the different cases, right? You make all 4 different cases until eventually, so you notice that here in this dump format, this is the left child, this is the right child, and this is an in-order traversal of the tree. And so it's required that you have these brackets, and the reason why the brackets help you is because it actually tells you which thing is the parent of which thing and everything like that, because otherwise, if we just outputted this, you couldn't tell if A is the parent or whatever. And the heights are the last element in this. It's the node name, the count, and the height. So basically here, you can just be like, okay, T, right? So if we insert T. And now let's insert Z, right? And so you see that this is what happens. So now let's check here and make sure that when we insert Z, what's going to happen is that instead of being the right child, T is going to come up and be the root, G is going to be the left child, and Z is going to be the right child. There we go. So, this is how to do it. Now, have I written the entire project yet? I have not. I just did the AVL part. It took me about an hour and a half to 2 hours to do, which makes me think that the project is going to take me somewhere around 4 hours. Let me just say that the project 1 took me around 1 hour. So adjust your expectations accordingly here, okay? Get to work early on this thing. I don't think there's any way that I can possibly be as scary as I need to be about this, okay? All right. So that's all I'm going to say about the project right now. I'm going to end class with a little bit of math, some kind of enjoyable thing. We're going to prove that the minimum number of nodes in an Avl tree of height h is f sub h, or it might be f sub h plus 1. I guess we'll figure that out in a second. Where maybe f sub, well, where fh is the Fibonacci, the hth Fibonacci number. Wow, I really can't write. So we're going to do this by induction. And I think that this is just a cute little proof. So let's assume, well, not assume, we want to do a base case. So the base case is going to be a single node in a tree, okay? The height of this is 1. Let's say that f of 0 is equal to f of 1 is equal to 1, and then f of n plus 1 is equal to f of n plus f of n minus 1. That's the definition of the Fibonacci numbers, right? Now, of course, you might be like, well, that's not the definition. It starts at 1 and 2. I don't care how you index. We're just going to call the 0th and the first Fibonacci number 1. And then the next one is going to be, it's going to be 1, 1, 2, 1 plus 2 is 3, 2 plus 3 is 5, 8, 13, isn't it 22? But that's odd, so it can't be 22. 21, right? See, I misremembered the Fibonacci numbers for a second. So then this is 34, and then this is 55, etc. So those are the Fibonacci numbers. So the base case is a single node of height 1. And is it true that the minimum number of nodes in a height 1 tree is 1? And the answer is yes, right? Because f1 is equal to 1. Okay. So now what we're going to do is we're going to assume this is true up to and including height h. So now what we're going to do is we're going to look at consider a tree of height h plus 1. Well, actually, the minimum number of nodes is strictly bigger than this, but yeah, but whatever. It's basically, so if we have a tree of height h plus 1, then we have this going on, right? This is a node, its height is h plus 1. It has a left subtree, and it has a right subtree, right? Yes. And my only assumption is that this is an Avl tree. So what is the rule for an Avl tree? The rule for an Avl tree is that one of these heights is h, and then one of these heights can either be h or h minus 1, right? Because the height can differ by 1, right? So if this height is h, then this height can either be, technically it can either be h plus 1, it can be h, or it can be h minus 1. Those are the three options for this. But we know it can't be h plus 1, because if it's h plus 1, then this is a height h plus 2 tree. So it can really only be h or h minus 1. Okay. Well, here's the cool thing. We're almost done. We invoke the inductive hypothesis. Now, the inductive hypothesis is that the number of nodes in an Avl tree is at most f sub h. So we know that in this tree, there's at most f sub h nodes, right? Or at least f sub h nodes. And in this tree, well, there could be at least f sub h nodes or f sub h minus 1. So let's pick f sub h minus 1. The reason why we pick that is because that's the minimum. And so we want the smallest tree possible. So here's the good news. F sub h plus f sub h minus 1. Technically, you have to add in this 1 for this root node. That's the minimum number of nodes in a height h plus 1 tree. And the good news is that you know that this is bigger than or equal to f sub h plus 1. And the reason why you know this is because this is the definition, right? That is the definition of the Fibonacci number f sub h plus 1. So basically this shows that if you have a tree of height h, for any h, you must have, and it's an Avl tree, right? An Avl tree of height h, it must have at least the Fibonacci number of that number of nodes, right? And so this is a beautiful fact. and I just wanted to share it. So, yeah. All right. So I think that's, I mean, and also it's a pretty simple example of induction, right? Because the base case is simple. It's a simple one-node thing. You assume it up to h, right? So that's your inductive hypothesis, is assume that it's true up until height h. Then you consider a height h+1 tree, and we've just proved that it's at least h+1. So the minimum number of nodes is bigger than or equal to f sub h+1, which proves that it's true for all, right? For all height h inside the natural numbers, right? An Avl tree of height h has at least, that's an easy way of saying it, has at least f sub h nodes. And that is just absolutely the best fact in this class. I think that really makes all of this tree stuff worth it. Okay, so now that I finished this proof, I will make myself available. I'll be around. Okay, because I imagine that some of you want help on your projects. If you're not done your projects, go do your projects. If you are done your projects, then you're done your project. Okay? So, all right, that's it. Let us hit the goodbye button.